Welcome to Biogas Basics. My name is Jürgen Kube, and this is the first presentation in a series about the substrate system of a biogas plant. This mini-series will explore rheological properties of digestate, pipe flow, pumps, pump connection, and feeding systems used in biogas plants. I will talk about digester mixing in the next mini-series. We start with the viscosity of digestate. What is the viscosity of digestate? I want to go beyond the generic answer of, well, that depends. I will describe what it depends on and want to give some tangible results which can actually help designing equipment in biogas plants. This is not a fluid dynamic lecture. I'll use simplified concepts to keep things accessible. The goal is to equip you with the knowledge needed to design effective mixes, pumps, and feeding systems for biogas applications. So, what is the viscosity of digestate? We start with some definitions. We have a two-dimensional velocity field. The coordinates are x and y. The velocity u is dx by dt. The velocity v is dy by dt and is 0 in this example. In this simple example, the shear rate is the derivative of u over y, which is the velocity gradient along an axis orthogonal to the velocity itself. The shear rate quantifies how quickly the velocity changes in the direction normal to its flow. The shear rate is high near mixers or pipe walls. It is denoted as gamma dot and has the unit 1 over time, typically 1 per second. The shear rate is different from the shear, which is a stress and has the unit Newton per square meter or Pascal. A laminar flow can be modeled as a collection of layers that are sliding on each other. The shear is the force required to pull one layer divided by the surface area of the layer. The shear tau is the force F over the surface area A. The viscosity is the derivative of the shear normal to the velocity of the layer. It can be written as tau over gamma dot. Now that we have defined velocity, shear rate, shear and viscosity, we can look into the viscosity of digestate. The first thing that should be noted about the viscosity of digestate is that it is not a constant, i.e., digestate is not a Newtonian fluid. Instead, digestate is mostly shear thinning. Its viscosity depends on the shear rate. The higher the shear rate, the lower the viscosity. We will talk about different models describing shear thinning fluids, but in a qualitative plot. They all look like the orange line. At low shear rates, the viscosity of digestate is very high, and only near high velocity gradients, for example near mixers, the viscosity will drop. This has significant impact on many phenomena at biogas plants. It is essential in the question whether stones and grit will drop out in the digester or pumped out with the effluent. It explains overheating of submersible mixes and foaming events. There are 4 relevant rheological models I will use in this presentation. I will explain them with this plot of shear stress over shear rate. The way the shear is measured as a function of shear rate is in a rheometer. A cylindrical chamber is filled with digestate or other fluids that must be assessed. In the middle of the chamber is another cylinder connected to a motor with a variable speed drive and a torque measurement. The device can measure the torque as a function of rotation speed. When the flow in the gap is laminar, the torque, rotation speed pairs can be converted into shear rate pairs. By plotting the shear over varying shear rates, we get the diagram shown here and can identify the rheological model of the fluid and its parameters. We also see the immediate problem with this experimental setup in AD. Digestate contains fibers that are of similar size as the gap in the rheometer, and this causes problems with the measurement. I will show different methods that can be used to estimate rheological parameters of digestate in later episodes of this series. The simplest rheological model is the Newtonian fluid. It is characterized by a constant viscosity. The viscosity is the slope in the shear rate, shear diagram, also called flow curve. The shear is viscosity times shear rate. The only Newtonian fluids in biogas plants is the biogas itself, compressed air and the hot water in the heating system. The simplest shear-dependent fluid is the power law fluid. The viscosity of a power law fluid is the flow consistency index K times the shear rate to the power of the flow behavior index n-1. If n is smaller than 1, the fluid is shear thinning. The exponent in the viscosity equation becomes smaller than 1 and the term gets smaller with higher shear rate. If n is 1, the exponent is 0. The shear rate to the power of 0 is 1 and the viscosity is constant. The fluid becomes a Newtonian fluid, and the consistency index is the viscosity. N can become greater than 1. In this case, the fluid is shear thickening, very rare in the AD industry. The flow behavior index is dimensionless, but the consistency index has the unit stress times time to the power of the flow behavior index. For example, If the flow behavior index is 0.7, the unit is Pascal, times second to the power of 0.7. Some digestates behave like a solid when they are not sheared. The flow curve does not start at zero, but is offset by the yield stress. A fluid with a yield stress behaves like a solid when it is sheared below the yield stress. Only if the yield stress is exceeded, the fluid starts to flow. Digestates in dry fermentation are characterized by a noticeable yield stress. They do not show the hydrodynamic stress state, which is defined by a tensor with only normal tensions of equal size and leads to flat surfaces in resting fluids. A non-moving fluid with yield stress can sustain shear stress, so it can show an uneven surface. The first presentation in the mini-series about mixing, presentation 12.1, will explain dry fermentation in more detail. The simplest model of a fluid with a yield stress is the Bingham fluid. In the shear rate, shear diagram, it looks like a combination of a Newtonian fluid plus a yield stress. If the shear is below the yield stress, the medium does not flow, and the shear rate is zero. Once the shear overcomes the yield stress, the medium starts to become liquid and displays shear thinning properties. The viscosity is the yield stress tau 0 divided by the shear rate gamma dot plus the term eta infinity, which is the viscosity at infinite shear rate. A Herschel-Bulkley fluid is a power law fluid plus a yield stress. It behaves similar to a Bingham fluid at low shear rates, but its viscosity decreases faster with higher shear rates. It is the most accurate rheological model, but it also has three parameters that must be fitted. The Herschel-Bulkley formula can be used to describe all fluid forms here. If tau 0 is 0, it is a power law fluid. If n is 1, it is a Bingham fluid. If tau 0 is 0 and n is 1, it is a Newtonian fluid. This shear rate, shear diagram, might look unfamiliar to many. After all, we are more interested in the viscosity, shear rate diagram. But in that diagram, all shear thinning fluids, that is power law, Bingham, and Herschel-Bulkley fluids, look very similar. It should be noted that there are many more rheological models. Leave scientists unobserved for too long, and they will come up with new and even more complicated models. For example, the rheological properties of some fluids depend on how much it has been sheared in the recent past. After a fluid has been subjected to a high shear rate, the viscosity of a fluid can be lower for a while because polymers have been disentangled, and the viscosity will only gradually increase to previous levels. This will lead to a hysteresis in the curves in the diagram. I will ignore those effects for simplicity's sake. Before I show the viscosities of digestate, I want to quickly discuss how the parameters are fitted. Let's say we measure the following flow curve. The best fit is the Herschel-Bulkley fluid, but it requires three parameters. We can directly read the yield stress at the value on the ordinate. The power law will also give a very good fit, but it will show a yield stress of 0. The Bingham fluid will give a decent fit at higher shear rates, but it can overpredict the yield stress significantly. Keep that in mind when using literature data for digestate. The type of model that can be used depends on the application and whether high or low shear rates are to be expected. So, what is the viscosity of digestate? I have plotted here the consistency index K and flow behavior index N for several digestates described in the literature. We can see that there is a correlation between N and K. This means, if we know N, we can estimate K with this correlation. But be careful, the ordinate has a logarithmic scale and the spread is roughly 1 to 1.5 orders of magnitude. Note that some data points are at n larger than 1. These are digestates that show a shear thickening behavior. Generally, the further left a data point is, the higher its viscosity, so shear thickening behavior is only observed in very thin samples. Now the consistency index contributes only partly to the viscosity. The other contributing factor is the yield stress, which is shown here as a function of the flow behavior index. We can see the yield stress does not correlate with the flow behavior index. It is 0 at n, larger than 0.9, but at lower flow behavior indices, some samples show an increasing yield stress, whereas others display a low yield stress or none. We also see a cluster of data points at n equals 1. These are the Bingham fluids. Remember that Bingham model will overpredict the yield stress if fitted to higher shear rates. And a power law fluid will underpredict the yield stress, as it is 0 by definition. So is there another data point that can be used to characterize the viscosity of digestate? The viscosity of digestate depends on the total solids concentration. We can first remove the Bingham data points and then replot the figure and allocate different colors to the data. The higher the TS, the darker the data point. we can see that higher TS leads to lower flow behavior indices N. For the yield stress, we have to rephrase the correlation slightly. High yield stresses are only observed at high TS in the digestate. Shear thinning digestates can be approximately described by the relationship. Decadic logarithm of K equals 2 minus 4.5 times N. Let's investigate the TS dependence further. We can use the parameters tau, 0, K and N to calculate the viscosity for a constant shear rate. I have chosen a high shear rate of 100 per second, so the impact of an overpredicted, Bingham, or underpredicted or power law yield stress does not have a high influence on the viscosity. Again, we can see a correlation between the logarithm of viscosity and TS, but the data points are spread in a window of roughly plus minus 2% in the TS or plus minus 1 order of magnitude for the viscosity. I can isolate the data points for certain groups of digestates, for example for agricultural digestate, i.e. mixtures of energy crop silages, manure and slurry. This makes the correlation slightly better, especially if we distinguish the samples further by their pretreatment. One set of samples uses the same digestate at different TS and different particle sizes. The experiments distinguish between untreated, coarsely milled and finely milled digestate, and within these groups the correlation between the logarithm of the viscosity and TS is linear. This means that the viscosity of digestate depends exponentially on the TS. This is in good alignment with other literature findings for particle suspensions. This exponential correlation is the reason why the digestate TS is often used synonymously for viscosity. The digestate TS is not its viscosity, and different digestates can have different viscosities and rheological behaviors at the same TS. But within one digestate group, the TS has a dominating impact on the viscosity. This allows the use of a mass balance to predict dilution streams, digester sizes, and residence times as explained in my presentation series about the mass balance, presentation number 4.1 to 4.3. The temperature has a small impact on the viscosity. The impact can be modeled with an Arrhenius approach, but the impact is small. The higher the temperature, the lower the viscosity, but there are occasions where the viscosity increases with temperature, for example in rye fermentations, which show a gelatinization of starch and other polymers in the digestate. But the overall impact of the temperatures is small compared to the impact of TS, so this information is more of academic nature. This next slide contains a lot of information, so let me walk you through. We created an artificial digestate. It is a suspension of screened sawdust with a defined particle size in a shear thinning carboxymethylcellulose, or CMC solution. The properties of the solution are shown in the table on the right side. The suspended solids, or SS, concentration is 11%. This is the mass percentage of sawdust particles added to the suspension. The particle size of the sawdust is 350 micrometers. The temperature is 40 degrees Celsius. The viscosity of the particle-free supernatant is 120 millipascal seconds at a shear rate of 20 seconds to the minus 1. Next, we kept all but one parameter constant, and then normalized this parameter and varied it between 0 and 100%. 100% value is shown in the right column. For example, the suspended solids concentration is varied from 0 to 14%. The mixture has 11%, which is 78.6% of the maximal value. For the temperature, 0% is 0 degrees Celsius, so a temperature of 40 degrees Celsius is 80% of the maximal value, 50 degrees Celsius. All viscosities are measured at a shear rate of 20 seconds to the minus 1, unless the shear rate is the variable parameter. Let's start with the impact of suspended solids. This is the orange curve. It can be nicely fitted with an exponential curve as described previously. Next is the impact of the particle size in green. We varied the particle size from 20 to 350 micrometers. The correlation of particle size to suspension viscosity can be roughly described as a power law correlation with an exponent of 0.28. The impact of the temperature in purple can be described with an Arrhenius approach. The impact of the shear rate, here in black, can be described with a power law approach. The flow behavior index of the suspension is n equals 0.55. Lastly, we investigate the impact of the supernatant viscosity on the suspension viscosity, here in blue. The supernatant viscosity is varied from 39 to 396 millipascal, which leads to an increase of the suspension viscosity from 880 to 3900 millipascal. While the impact of the supernatant on the suspension viscosity is not proportional, the supernatant viscosity increases by a factor of 10, whereas the suspension viscosity increases by a factor of 4.4. the viscosity of the suspension increases more than just the viscosity of the supernatant in absolute terms. The presence of particles amplifies an increase of the supernatant viscosity. We can repeat the experiment for different suspended solids concentrations. The suspended solids concentration was varied from 7% to 13% in 2% steps. Especially at elevated suspended solids concentrations, the impact of the supernatant viscosity on the suspension viscosity is very high. This phenomenon can explain how enzymes reduce the viscosity of digestate despite having little impact on the suspended solids concentration. The enzymes merely attack the solubilized biopolymers, and this reduces the viscosity in the supernatant, and as a consequence also the viscosity of the suspension. It also explains how diluting the digestate with fresh water reduces the viscosity of the suspension further than diluting it with process water, i.e. separated digestate. Fresh water also dilutes the viscosity in the supernatant, whereas process water only reduces the concentration of suspended solids. Let's conclude. The viscosity of digestate is not a constant, but depends on the shear rate. Digestate is normally shear thinning. It becomes more liquid near high velocity gradients, for example near mixes or pipe walls. Some digestates, especially those that have a higher viscosity, show a yield stress. A digestate with a yield stress behaves like a solid when it is subjected to shear stress below the yield stress, and only liquefies when the shear stress is above the yield stress. For example, it can be a solid in the middle of a pipe flow and a liquid near the pipe wall. More on this in a later episode. The presence of a yield stress in digestate is also a good definition of a dry fermentation. We introduced different rheological models: Newtonian, power law, Bingham, and Herschel-Bulkley fluids. All but the first are shear thinning, and the latter two are characterized by a yield stress. When fitting model parameters, beware that a Bingham fluid can overpredict the yield stress if fitted to higher shear rates. Similarly, a power law model can be fitted to a flow curve of a fluid with a yield stress when data points at low shear rates are omitted. Ideally, we use the Herschel-Bulkley model, but it has 3 model parameters, and a wide range of experimental data is required to fit the parameters. When choosing the Rheological model, think first what ranges of shear rates are expected in the application that requires the model. When we plotted literature values of flow consistency index and flow behavior index, we got a good correlation in the log K N diagram. That means if we can somehow measure the flow behavior index N, we can roughly estimate the order of magnitude of the consistency index. I will show some approaches on how to measure N in later episodes of this mini-series. Unfortunately, there is no clear correlation between yield stress and flow behavior index. Yield stress can, but does not have to occur when the flow index is 1 or lower. There are also examples for low yield stress at very low flow behavior indices. The total solids concentration is an important parameter of the viscosity of digestate. When Ts rises, the consistency index increases and the flow behavior index decreases. Higher Ts digestates show also higher yield stress, but a high Ts does not automatically lead to a high yield stress. Within a digestate group, the Ts has an exponential impact on the viscosity. This is the reason why digestate Ts is often used synonymously for viscosity. But when the type of digestate changes, the Ts cannot be used for viscosity prediction. Digestates from food waste, sewage sludge, paper mill waste, and energy crops have different viscosities at similar Ts. Particle size has an impact on the viscosity. When digestates are macerated or milled, their viscosity decreases. The viscosity decreases with increasing temperature, but the impact is only marginal compared to the Ts. The classical correlation is the Arrhenius fit, but some digestates show a different behavior if chemical reactions occur in the digestate, for example gelation or gelatinization. Lastly, the viscosity of the supernatant plays an important role on the viscosity of a suspension. A viscous supernatant amplifies the viscosity of the suspension. This effect explains how enzymes can reduce the viscosity of digestate without reducing the concentration of suspended solids, and why the addition of fresh water reduces the viscosity further than the recirculation of process water. Here's an overview of the literature used in this presentation. Pause the video if necessary. This presentation focused on the rheological basics and on parameters that impact the viscosity of digestate. In the next couple of presentations, we will use these fundamentals to investigate the impact on pumping and mixing digestate, predict and prevent sedimentation, flotation or crust formation and foaming, in short, all processes that are impacted by the viscosity of digestate and its shear thinning property. I hope you learned something new, and I see you in the next episode of Biogas Basics.